Welcome to this lesson dealing with logarithmic functions to any base. It's primarily aimed at maths methods 3 and 4 students, but could be equally useful to anybody studying maths to a higher level. During our previous lesson, we were looking at the idea of graphs, to any base. So, for example, y is equal to 2 to the power of x, and we discovered that it crosses here at a value of 0, 1. Why? Well, if we have an exponent to a power of 0, we know that anything to the power of 0 is equal to 1. So the basic graph we're given by y equals 2 to the x would cross at 0, 1. We also have an important benchmark point that when x equals 1, I would be able to find this point relatively easy because anything to the power of 1 is the base number. So we now know that this has a crossing point at 1, 2. As a reference now, if we have that basic idea, we should be able to look and be able to give the general graph of y equals 10 to the power of x. Again, if x equals 0, otherwise meaning on the y-axis, it's still going to cross through here. So roughly speaking, it's going to do that. But I now suggest it's going to go up a lot quicker. Why? Well, imagine what will happen when x is equal to 1. Y then becomes equal to 10, which puts it significantly higher up. So there we go. So we can now imagine that's at 10. And so our crossing, or our second point, will be 1, 10. That was our general idea of exponents to any base, or graphs to any base. And we then went on to reflect and dilate and translate them in the previous sections. How does that now relate? If you've seen our previous video with regards to inverses, we found out that if we have the line y equals x and we have a one-to-one function, when we do an inverse, what we're actually doing is reflecting it in the line y equals x. So how does that work with what we've currently been doing? Well, let's look at the graph y equals 2 to the x. That looks something like this, where we know that crosses through 0, 1. If I was to algebraically look at the inverse of this function, well, we would then say, well, where there is an x, put a y, and where there is a y, put an x. And we would now try and solve that. Well, using our logarithm rules from previous sections, we would now be able to write that as log base 2 of x is equal to y. But we also know that the inverse of a function is given by a reflection in the line y equals x. And we know that the range of one becomes the domain of other, the domain of one becomes the range of the other, and this point here reflects or translates over to here. And that seems fairly obvious as well, because if I have 0, 1, and I'm letting the x value be the y value and the y value be the x value, then just swapping them over tells me that this now is going to look something along those lines. So if this was the graph 2 to the x, this now becomes log base 2 to the x, and they are a reflection of one another. So tying this all together seems to be quite helpful because it's now given me the general graph of y equals log 2 to the x. And hopefully you'd be aware that if you had the graph of log base 10 to the x, that would still pass through this point here, but it would just be narrower or closer to the x-axis. All right, but that's not our scope at the moment. So, using the ideas of inverses, we now have the general shape of a graph of log base anything to the power of x. It looks pretty similar to this. How are we now going to use that in methods? Well, much as we did before, we're going to look at Dr. T. If you remember, Dr. T stands for dilation, reflection, and translation. So imagine we have the function y equals 2 log to the base 2 of x. How is that going to look? Well, in the same way as we've done previously, this value in front is going to be a dilation of factor 2. So it's important to write dilation. It's important to say what factor it is, and this is going to be away from the x-axis. All right? Because it effectively squidges it or stretches it that way. All right? Quick sketch then. If that was our standard, then this would still pass through this value here, remember? But it would look more like that. So it's stretching away from the x-axis. That's if it's multiplying the whole function, for example. What happens if we have y is equal to the log base 2x? Well, if you remember back to quadratics where you have x minus 2 squared, what does that look like? Well, it doesn't move it 2 places that way, if you remember, contrary to the minus, it moves it 2 places that way, or it does the opposite of what we're expecting. So automatically, I know that this has a dilation of factor a half. All right, it's the opposite. It's not double, it's actually a half, and this time away from the y-axis. All right, it's a dilation of factor half away from the y-axis. So this actually squidges it closer. So remember, inside or by the x, it's the dilation factor a half away from the y-axis. Outside, it's the dilation factor, whatever it gives, from the x-axis. So that's dilations done. What about reflections? Well, again, we've got our standard value looking something along these lines. And actually, if you remember, that looks sort of like the graph of root x. But remember, whereas root x starts at 0 and has no negative component in the y, yep, this does. All right, it goes up and across. So let's look at our reflections. Well, if we had the graph of log 2 to the x, but this time we have a minus sign in front of it, what does the minus sign do? Well, as it's done previously with all the other functions we've done, this minus is a reflection in the x-axis. All right, it's a reflection in the x-axis. So what would that do? Well, yep, it would make it look something similar to this. Still crossing at that point there at 1, 0. All right, so it's a reflection in the x-axis. What would happen if we had y is equal to the log 2 of a negative x? Well, if the negative is in beside the x, and be very careful there because there are a number of tricky questions, that is a reflection in the y-axis. All right, so in this situation, that would look something similar to this. This time, that would cross at the point -1, 0. All right, so the negative sign, keep an eye out for it. It's important. So that's now reflections considered. How about translations? Pretty much the same. Let's do the easy ones first. If I have log base 2 of x plus 3, that is external to the log 2 of x, and so that is a vertical translation of 3 spaces. All right? So if I have my standard graph looking like that, what would this look like? Well, hopefully speaking, it would look something, well, like that, where this would no longer cross through 1, 0. And if we now look at the idea of what happens if the value is inside, if we have log base 10 of x plus 1, well again, this inside would give you the suggestion that it actually moves 1 place that way, but it doesn't. It moves 1 place this way. It is the opposite of what you're expecting when it's inside the function. So this will now have an asymptote, right, here, where x is equal to -1, and my graph would look something similar to that, where this time that would cross at the origin. And if you think about it, if the standard graph crosses at 1, 0, and you're moving the whole graph that way by 1 position, it will cross at the origin. If you have to find other crossing points, for example, then you know that you have to substitute in. This is a really quick gallop through this as an introduction. All right, so hopefully you will now spend the lesson working on the questions in the textbook. We'll deal with the spassa at this moment in time and review more on that on Friday. All right, thanks very much. I look forward to seeing you later on in the week.